Hello, my brilliant students, and welcome back. I know, board exams are just around the corner. And this chapter, electrostatic potential and capacitance, can sometimes feel a little complicated, but don't you worry at all. We're going to make it so simple you'll be feeling like a pro in no time.
So, namaste, my dear students. First things first, take a nice deep breath. Let go of all that exam tension. Bilkul tension nahi lena. Think of this as our special, quick revision session. We are going to master this chapter together. Ready? Chalo, let's jump right in.
Okay, so here's our game plan for today. First, we'll understand what electrostatic potential really is. Then, we'll see how to calculate it for different charges. After that, we'll find a way to actually see these potential surfaces. Then comes the super important topic of capacitors, and we'll even solve a problem together to build your confidence. And finally, a rapid-fire revision of all the key formulas. Sounds like a plan? Let's go.
Right then, first up, what on earth is this electrostatic potential? Well, think of it like this. Imagine an electric field is like a big hilly area. Every single point on that hill has a certain cost to get to. It takes more work, more energy, to push something uphill, right? Well, that cost of being at a certain position in an electric field, that's what we call potential.
Now, let's connect this to something you already know. Yaad hai? Back in class 11, you studied gravitational potential energy. That was just the work you did to lift, say, a heavy book against gravity. Well, electrostatic potential energy is literally the same idea. Instead of lifting a mass against gravity, we are pushing a charge against an electric field. Simple, na? It's the same logic.
Okay, so that was potential energy. Now, what about just potential, written as V? Now, you can see the long textbook definition here, but let me give you the simple secret for your exam. Just remember the formula. Potential is simply the work done divided by the charge. That's it. V equals W by Q. It tells you how much work it costs per unit of charge to be at that spot.
All right, so we know what potential is, but how do we actually calculate it? And does it change if we have just one charge, or maybe a pair of charges, or a whole bunch of them? Let's check it out.
Now, look closely at this graph, Bachcho. This is super important. For a single point charge, you can see the blue line, that's potential. It slopes down nice and gently. It decreases as 1 by R. But now, look at the black line for the electric field. Whoosh! See how steep it is? It drops off so much faster as 1 by R squared. This comparison is a classic exam question, Beta, so please remember this picture.
So let's summarize this. For a single point charge, potential falls as 1 by R. Easy. But what about an electric dipole, with a positive and a negative charge together? Well, for a dipole, the potential falls off way faster, as 1 by R squared. And there's another key difference. For a dipole, it also depends on the angle. This table makes the difference really clear.
And what if you have lots and lots of charges? Don't panic. This is the best part about potential. It's a scalar quantity. That means no vectors, no directions, no headache. Thanks to something called the superposition principle, you just add them up. That's it. The total potential is just V1 plus V2 plus V3 and so on. Easy peasy.
Now, we know what potential is, but the thing is, it's invisible, right? So how can we actually get a picture of it in our minds? Well, the answer is something called equipotential surfaces. Just think of them as contour lines on a map that show you the different heights of a mountain.
Right, so the big question is, how do we actually visualize this? How can we see this invisible property of space that's all around a charge?
We see it using equipotential surfaces, and the name tells you everything. Equi means equal, and potential means, well, potential. So it's a surface where the potential is equal at every single point. And here is the golden rule, bachon. You must remember this. No work is done to move a charge on an equipotential surface. Zero, because you're not going uphill or downhill.
And here's what they actually look like. These diagrams are straight from your NCERT textbook for a reason. They are very important. For a single charge on the left, it's simple, right? Just perfect spheres around it. But for a dipole on the right, see how the shapes get a little more complex, a bit squished? Make sure you know how to draw these.
So we've talked about all this potential energy. But is there a device that can actually, store it? Absolutely. And that device is called a capacitor. Seriously, the best way to think about it is like a tiny little power bank. But instead of storing battery power,
It stores electric charge and energy. And this is the most famous one, the one you'll see in all your problems, the parallel plate capacitor. Look, it's so simple. It's just two metal plates facing each other. You put positive charge on one plate, negative charge on the other, and boom, you've stored energy right there in the electric field between them.
So, how do we measure the storage ability? We call it capacitance, or C. And the formula for it, this is the superstar formula of this topic, so pay attention, is right here. C equals epsilon naught A divided by D. Epsilon naught is just a constant, A is the area of the plates, and D is the distance between them.
So, just by looking at that formula, how can we make a capacitor stronger? How can we increase C? Well, first, look at A on the top. If we make the area bigger, C gets bigger. More area, more storage. Now look at D at the bottom. To make C bigger, we need to make D smaller. So just bring the plates closer together. It's all about area and distance.
Okay, enough of the theory. The real confidence for your exams comes from practice, right? So let's solve a classic problem together straight from your textbook. Don't worry, we'll go step by step, and you'll see how easy it is.
All right, problem time. This is example 2.1. So part A asks us to calculate the potential, V, at a point that is 9 centimeters away from a given charge. Then, part B asks us to find the work done to bring a new, smaller charge to that very same point. It's a perfect two-part question to test what we've just learned.
Okay, let's do this. For part A, we need potential from a point charge, so we use our formula. Now we just plug in the numbers. But be very careful. The distance is 9 centimeters. We must convert that to meters, so it becomes 0.09. Do the calculation and we get our potential. 4 times 10 to the power 4 volts. Part A is done. Now for part B, we need work. Remember our very first formula? V equals W by Q? So we just rearrange it. W equals Q times V. We already found V, so we plug that in with the new charge, and there's our final answer. 8 times 10 to the power minus 5 joules. See, not so scary when you break it down.
Wow, we've covered so much. We are almost at the finish line. Before we end, let's do one final super quick revision. Think of this as your formula cheat sheet for the exam. These are the ones you absolutely, definitely have to know.
Okay, ready? Let's go. First, the basic definition of potential. V equals work over charge. Second, potential from a single point charge. Third, the definition of capacitance. C equals charge over volt. Fourth, our superstar formula for the parallel plate capacitor. C equals epsilon naught A by D. And finally, potential energy. U equals Q times V. That's it. These 5 formulas are the heart of this chapter.
And that's it. We're done. Listen to me, my dear students. Please don't take any stress. You have studied so hard and you have prepared well. You know this material. Just go into that exam hall with a calm and confident mind. Trust in your knowledge. You are going to be fantastic. All the very best from my side.